We are discussing about closed loop control of DC drive. So in my today's class, only few slides are pending. Okay, so which one the based on that AC motor drives. Okay, so we are aware about the very basic limitations of different DC motor drives. Basically, the control of the DC motor drives is quite better. Okay, means better in that in sense of what in sense in terms of sometimes you can see the simple controlling method. Okay, so you can say like that control is comparatively simple than your AC motor drives, but other problems also be there. Suppose you are suppose you are prepare you want to some other issues, suppose maintenance cost and insulation breakdown chances. Okay, there is a commutator segment, so short circuit chances in your commutator segment, so other kinds of reasons also be there. So that's why you have to switch to AC motor drive. Suppose induction motor if you are using. So now here we can see in this work, so you are directly using that induction motor drives. But the problem is that not problem right now, that recent technology is such a manner that what kinds of motor you are using, so they are controlling the motor in the vector control mode. Okay, so in vector control mode, what advantages you can see, you can observe that there are different types of transformations. Okay, so different types of transformation may cause for or again dq axis transformation. So overall working will be, maybe motor is different, maybe motor is AC motor, but working principle is based on that quite of DC motor scheme. Suppose if you transform all those parameter in dq axis, so more or less controlling method sometimes it's quite easy to handle, and other benefits you can also get from that machines or controllers. Okay, so this basic reason you are getting from there for why you are using AC motor drives over the DC motors. Okay, so what are the important thing, that AC motors, okay, AC motor exhibit highly coupled, okay, highly coupled non-linear and multivariable structures as opposed to so much simpler decoupled structures of the separately excited DC motor. So you can understand. So that I am talking about that transformation, DQ transformation, direct axis transformation, quadrature axis transformation. So controlling may be simple, but in case of AC motor, they are controlling in the terms, controlling is complicated compared to DC motor. The control of AC drives, okay, the control of AC drives generally require the complex control, okay, complex control algorithms that can be performed by microprocessors or the microcomputers or microcontroller along the fast switching power converter. So control is more or less same. Basically, same means technology may be different, but in terms of control. So in last class we discussing about how the closed loop control is performed. Okay, so in this perspective you can say like the same type of fundamental thing you have to sense the motor speed, then entering that motor speed to scaled value through the DAC controller, digital to analog converter inside of the computers, and now you are processing them, and end of the day you are driving the switching devices to controlling the speed of the motor. Okay, whatever it may be the AC motor, it may be the DC motor. The entire philosophy is simple, but processor working processor simple. Idea the how it is working, that is simple to understand, and rest of the thing will be based on your controlling technique. For which motor which type of techniques are required, so we can do it. Okay, the AC motor have a number of advantages. Okay, the AC motor have a number of advantages. They are lightweighted, okay, like 20 to 40% lighter than the equivalent DC motor. So lightweight means again that burdens are going to be less, so efficiency means power losses chances also been less. Okay, are inexpensive and the have low maintenance compared to the DC motor. So that's why I'm in my all the time I'm talking about the cost effective. So inexpensive and low maintenance. Okay, maintenance cost also less compared to the DC motors. Okay, they require control of frequency, voltage, and the current for variable speed applications. Okay. So the additional parameter you are getting for DC motor, what you need to do, you can only vary the armature resistance, field resistance, okay, and the voltage, armature voltage. But here you can, so you are again another options also be there. You can controlling the frequency. So similar type of things also be there. So constant torque operation, constant power operations. Okay, so in constant torque operation, if you see the VF characteristics, V by F waveform. Okay, so you want to try to make it by V by F waveform. So V by F ratio should be keep constant in up to the base speed. What will be the problem if you are not making it constant? So normally what we are doing, so we are making the power is constant. For the machines, what we are doing, we are making the flux. Okay, more or less flux you are trying to make it in constant means linearly varying. Okay, not the non-linear varying. So if that V by F ratio is not maintaining the linear ratio, so you can say like that they are non-linearly, they are varying non-linear manner means there is a high chances for the saturation of the flux. Okay, if there is a flux saturation, so so some protections in case of motor, we are giving some low voltage protection as well as there is some protections also given that flux saturations. Okay, so the flux should not be saturated. So if the flux saturated, so there is a high chances for that inserting of the non-linearity to the system. So that is not expected. Okay, so that is not expected and appreciable. So that's why you try to maintain that V by F is constant. Okay, so the increasing of the flux is linearly varying, more or less constantly varying. Okay, up to certain level. After that, you can understand that BH loop. So after some time, whatever it goes to the saturation. So up to base speed, your constant torque operation. So where V by F should be constant, that means flux should be constant up to that base speed. Then if you want to change the speed of the motor above the base speed, what you need to do, you have two categories. So you can recall the power electronics subject, power electronics. So one is your AC voltage controller, another one is your cycloconverter. So in case of AC voltage controller, you can only vary the magnitude of that output of the converter. So okay, frequency you are not able to vary. But in case of cycloconverter, magnitude, output voltage magnitude you can also vary, as well as frequency of the output voltage that can also be varied. So both amplitude and that frequency can be varied in case of cycloconverter, but in case of only in case of AC voltage controller, only voltage amplitude you can vary, and other thing you are not able to vary them. Okay, so power converters, inverters, and AC voltage controller can control the frequency, voltage, so frequency, voltage to or current to meet the drive requirement. Okay, so inverter can control frequency also. Okay, so you know that we are using inverter, so DC to AC conversion. So previously in locomotive they are using that Arno converter. So Arno converter concept is that they are converting that single phase to three phase conversions. But now you know that inverters are already there in your system. So you are not using that Arno converter. Arno converter is a machine. Okay, so that is obsoleted right now. So now what you are using inverter directly conversions of your DC to AC. And respective filter winding you are also using to get the proper appropriate money, maintaining that performance index of that converter. Okay. Then what are the other important things that introduction the AC motor does? These power controllers, what are the following points? These power controllers which are relatively complex. Okay, that I am talking about the AC voltage controller and cycloconverter. So AC voltage controller, sometimes it may be simple to operate, simple to design, but in case of cycloconverters. Their circuit also circuit is not so much complicated, but operations and the controlling are very complicated. Okay, the power controllers. Okay, the power controllers which are relatively complex and more expensive require advanced feedback control techniques such as model reference, the set point tracking that I am talking about, adaptive control, sliding mode control, and the field oriented control (FOAC). Okay, so you can understand their behavior. Controlling behavior is complex, so that is not acceptable for AC motor. Quite difficult for that AC motor drives. Okay, quite difficult for controlling your AC motor drives. Okay. So what are the different types of drives we are using for it? So we are using the synchronous motor drives and induction motor drives. Two drives are using. Okay. Induction motor drives and synchronous motor drives. Okay. As the AC drives are replacing the DC drives are used for the mainly the industrial and domestic applications. Okay. So normally you are using where industrial application and the domestic application, and different two types of drives we are talking about, induction motor drives and synchronous motor drives. Okay. The controlling of the model reference, adaptive control, sliding mode control, and field oriented control. These are the some controls are there. Complex and more expensive. Okay, required to advanced feedback control. Okay. In case of induction motor drives, you can see the torque speed or torque slip characteristics. Okay, it is your torque. Okay, it is your torque and y-axis, and slip is in your x-axis, slip or speed. Okay, so now you can see the slip is varying -1 2. This is -1 0. This is 1. It is your slip, and it is 2. And speed is your, you can see it is 0. 1 slip means omega. Sleep equal to how much value? Sleep equal to 1 means you can understand how much value is it. So speed equals to almost 0. Okay, speed is 0. This is minus synchronous speed, then synchronous speed twice of the synchronous speed. Okay, so you know that formula of that sleep. So from the sleep you will replace them, so you will get the expression of the speed. So from the 0 sleep, okay, gradually you are increasing, linearly varying, then maximum torque you are reached, then automatically it is gradually decreasing. Okay, and speed also, here you can see 0, then omega speed, synchronous speed, then automatically here your speed is 0 and goes to minus synchronous speed. And the direction of rotation will be different. Here you can see rotation is in your clockwise. So first clockwise rotation you are considering synchronous speed, motor speed also in clockwise. Here you can see which one speed is motor speed is reverse. Okay, so yeah, or synchronous speed WS is the same direction, but omega n will be reverse. That means it is reverse plugging. Okay, this is your forward braking conditions. This is reverse plugging braking, reverse plugging conditions, and forward regeneration is there in the next quadrant. Okay, so here you can see your maximum torque. Okay, slip is maximum. Okay, minus sm and -1, and it is twice of your synchronous speed. Okay, and but directions are same. Okay, omega s and omega m motor directions and that synchronous speed. So both are in motor speed and synchronous speed, both are in the same directions. Okay, so this the speed torque characteristics of induction motor drive. So speed control techniques. Okay, speed and torque of the induction motor can be controlled by what are the conditions? Stator voltage control, rotor voltage control, okay, frequency control, stator voltage and frequency control, and finally stator current control. So total 5 methods are there for controlling the speed. Okay, so stator voltage control means you are using the auto transformer. Okay, it may be single phase or 3-phase, but 3-phase induction motor is not the self-starting. Okay, so in this case you have to capacitor run, starter is required. Different starters also be there, and single phase 3-phase induction motor also some starters that they call, normally we are using dual starter or star delta starter. Okay, so stator voltage control means you are using some auto transformer in the stator end, and you are varying that auto transformer. You are able to varying the auto transformer terminals. Okay, that there is a changing slider is there. You are varying that point, so automatically the stator voltage also control. So if you recall the drives syllabus, you can write down that formulas are there. So one big formulas are there where you can see directly the stator voltage is proportional to the speed of the motor. Okay. If you are able to vary the stator voltage, automatically motor speed also vary. Voltage, rotor voltage control. So now we are going to control the rotor voltage. Okay. Frequency control also be possible. Okay. That VYF control in the frequency. Frequency control only possible after the base speed, not below the base speed. Okay. So below the base speed if you are doing, but there is a high chances for going that flux to the nonlinear zone. Means changing of your input, there is no changes in the output. Okay. So stator voltage and frequency control, that both control can be possible, okay, by making the fluxes constant. Stator current control. So stator current control also be possible to change, okay, stator current. So that may responsible for changing the flux of that stator, okay, and automatically you are able to change the speed of that motor, okay. To meet the torque speed duty cycle of a drive. Okay, to meet the torque speed duty cycle of a drive, the voltage, current, and the frequency control are the normally used. Okay, so these are the simple thing. Changing of voltage, that normally you can change the duty cycle. So other important points of that induction motor drives, what are the other points? Here you can see the stator voltage can be varied. Okay, stator voltage can be varied by three phase. Okay, what are the three phase? AC voltage controllers are there. AC voltage controller, you can only change the magnitude. Voltage fed variable DC link inverter. So inverter input is DC, but output is AC. Okay, the pulse width modulation inverter. So you can also increase the you can also use the PW inverter. Okay. However, due to the limited speed range, okay, however, due to the limited speed range requirements, the AC voltage controllers, okay, AC voltage controllers are normally used to provide the voltage control. Okay, used to provide the voltage control. The AC voltage controller are very simple. Okay, AC voltage controllers are very simple. Okay, so you can easily vary the magnitude. That instead of variac. Okay, instead of variac, you can also use the AC voltage controller. Okay, automatically, if you are able to vary the gate pulse, so output of that controller also will vary. Okay, so however, the harmonics contents are very high and input power factor of the controller is low. Definitely harmonic high means power factor also be low. Okay, so also be less. Basically, high power factor may cause for high reactive power. High reactive power cause for reduction of the power factor. Okay. So however, harmonic controls are very high and input power factor of the controller is low. So harmonics high, so that may cause for more values of filter parameters. More values of filter parameters means system will be bulky, costly, heavy. Okay, any aspect, and also for basically you are not able to neglect the harmonics. Anyhow, reduce the magnitude of the harmonics, but if it is not coming, sorry, so it's difficult to work. Okay, so they are used mainly in the low power applications such as fan, blowers, and centrifugal pumps, where the starting torque is low. Okay, so starting torque is low. That's why AC drives is using for this moment. But right now, recently, most of the most of the cases, okay, they are using AC motor. Okay, DC motor also with the attraction motor, but number of motor is quite less. Okay. They are also used for starting high power induction motor to limit inrush current. Okay, so that one storage elements are there, so that may also give some benefits at the time of inrush current. Okay. Here you can see the induction motor drives for rotor voltage control. So you are using that rotor concept. RX3 equal resistance values are given in the rotor windmill, and here you can see the torque speed characteristics. So this one is your torque speed characteristics. The speed both are reverse directions. Okay, so slip are there and increasing of the R. Okay, R is increasing. Okay, in wound rotor, the external three-phase resistor may be connected to a slip ring. Okay, connected to a slip ring is shown in the figure. The development torque may be varied by the varying the resistance Rx. If Rx is referred to the stator winding added to the RR, equation may be applied to determine the developed torque. Okay, so you are getting the developed torque. The typical torque speed characteristics for variations in that rotor resistance are shown in the figure. So that very common figure. So you know all of you are aware about it. Three-phase supply, stator, rotor is there. Inside stator three winding, rotor three windings are there. So if your Rx is increasing, you can see that speed. Okay, speed is increasing fastly, and you are getting that that. Synchronous speed you are attaining very good. So by changing that rotor resistance, so you can limiting the current carrying flow to the machines. Okay, so more load means you can that may cause for high current, so that you can rate through this machine through these characteristics. Okay, this method increase the starting torque while limiting the starting current. Okay, so limiting the starting current is required. Okay, protections over current protections are there. However, this is an efficient method, and where would be the imbalances? Okay, where you can see the imbalances in the voltage and current if the resistance in the rotor circuit are not equal. So rotor circuit resistance are not equal, so imbalancing will be there. Okay, so wound rotor induction motor is designed to have the low cost, low rotor resistance, so that running efficiency high and for full load speed. Okay, so these are the different benefits you can getting from that induction motor drives by using rotor voltage control. Okay, so rotor mirror motors, okay, are widely used in the application requirement application requiring frequent starting and braking conditions for large stock. Suppose crane highest large stocks are there for the starting condition and braking condition. So that's required for that one. Because of the availability of the rotor winding for the changing of the rotor resistance, the wound rotor offer the greater flexibility to control. So definitely, it having wound rotor having additional resistance, you can control the additional resistance from externally. Automatically, their load carrying capability will be more, better starting current conditions. These conditions will get better to wound rotor motor. However, it increase the cost and need maintenance due to slip ring and brushing. So definitely, you have to maintain it, so it may costlier. Okay, and wound rotor monitor is less. Wound rotor motor is less widely used in compared to the squirrel cage motor. So motor also will less use, so demand is not so much high. Okay, so you'll get some more benefit from that one. Okay, so here you can see that induction motor drive for rotor voltage control. Okay, so just for hello Pritish, I am in a class. Tell me. Print out of which one? Print out of which document? Okay, okay. You send it to me in WhatsApp. I'll print it out. Okay. Hmm. Okay, so here you can see the So here you can see that induction motor, rotor, and you can see the stator, both are there. Three-phase supply is there to the stator. But what happened in previous case, if you controlling the resistance, okay, so that you can see here you can see the resistive path is there. Okay, if you are able to control it, okay, by variations, here is there is a variant. So if you are able to vary it, then what happen, huge losses will be there. So what you can do for the cost efficient condition, so you just change it. Okay, what you will do, so you just replace all those things. Okay, you just replace all those variable resistance by a soft switch. Okay, so switch is there. Okay, so on switch is there, what you will do, the rotor is there, its CPS supply is there. Now you just rectify that supply. Okay, rotor also in AC, you are using bridge. Okay, so you are make them, you are rectify them. Okay, so you will get the DC value over there. Okay, now what you will do, you will just controlling like T on a duty ratio control, like that thing. Okay, so duty ratio control, if you control over there directly, that value will be reduced. So you can see some concept also be there. Suppose you know that rotor energy can be feedback to your rotor energy can be feedback to your main bus also by this way. Okay, so your current is there. Okay, so in smoothing reactor is there, so you can do it through that path. Okay, resistance is there, VDC, you will get it. Okay, so three-phase resistor. Okay, three-phase resistor may be replaced by three-phase diode rectifier. So just previous I am showing you the three-phase resistor. Now it is replaced by the diode rectifier. Okay, and the DC converter. So shown in the figure where gate turn-off thyristor you are using GTO, or can insulated gate bipolar transistor IGBT, you can also operate the DC converter switch. Okay, now inductor LD is acts the current source ID, and the DC converter series effectively resistance, which can be found from the equation. So equations that are equal to R into 1 minus K. K is your duty cycle that I am talking about it, T1 by T. So by varying of the K, so you can control that effective resistance. Okay, so loss minimizations actually you are doing for this conditions for reducing the loss of the DC converter, and the motor speed can be controlled by varying the duty cycle. Okay, so you are varying the duty cycle. These portions of the air gap power, okay, this portion of the air gap power which is not converted into the mechanical power, called the slip power. Okay, so you know that which one is mechanical power, which one is the slip power. In the machine you are elaborately already gone through it from the machine. So slip power is dissipated in that S, so in that R. So this is also called the slip power recovery. Okay, that slip power is dissipated in the R. That slip power can be feedback to your main bus. Okay, and you can utilize the power. So that's why one also terminology is there, that is called slip power recovery. So here you can see the slip control by the DC converter. So the without doing lot of loss, you can control it. Okay. So the motor torque and the the motor torque and the speed. So here you can see the motor torque and the speed of the induction motor can be controlled by the changing of the supply frequency. Okay, so V by F control. After beyond the base speed, you can control by the changing of the supply frequency. We can notice from the equation that the rated voltage and the rated frequency, the flux is rated value. So all the things are rated. If the voltage is maintained fixed, okay, voltage maintained fixed, the rated value, while the frequency is reduced below, okay, to its rated value, the flux increases. Okay, flux can be increased. This would cause the saturations of the air gap flux. Okay, and the motor parameter would not be valid in determining the torque speed characteristics. Okay, so at low frequency, the reluctance decrease and the motor current may be too high. So low frequency reluctance decrease. So you know that XL equal to pi FL, reluctance is, decreases. So automatically the current will be very high. So there is a chances of the induced current. So for type of frequency control, normally it is not normally used. That's why you can only do for it constant power region. Okay, P equal to T into omega, torque into omega. So where you are able to do that frequency control. So this is overall idea about your DC drives and AC drives for controlling the speed of your traction motor. So some of the portion is already attached with your power electronics converters, and some of the most of the portion is attached with your power electronics converter, and that portions, most of the portions you have already gone through in your earlier subjects, suppose machine, power electronics and drives. Okay, so I'm just giving some very brief about brief recap. Okay, I'm very brief about the recap. Okay, so after that we can do it. So okay, so it is really, really important for the tractions. Okay, so and they are very important for our some questions at the time of exam that maybe come to here. Okay, so these are very important topics. Okay, basically the power electronics converter control your DC drives as well as AC drives. Very important topics for the tractions. Okay, I hope all of you are able to understand. Do you have any kind of query? You can ask me. So we can some of the portions can be rediscussed. Okay, do you have any query on it? Huh? I'm in lab class, no? So please wait for a moment first. Hello, I hope you do not have any query. Okay, so if you have any query, you can ask me. Okay, so almost one submodule is completed for the traction. Okay, so from my next class, we can start from another segment. The traction is not totally completed, partial portion is already completed.